Happy Wednesday. So anyhow, you guys can read this. It's self-explanatory. No class next Wednesday. Take-home exam will be given on Monday. It is due Wednesday. Very good. Email me with any questions. So on Monday, we spent a ton of time thinking about choosing cards from a standard deck. And what the purpose of what I was doing, and I don't know how effective it was, perhaps many of you left more confused, and for that, I'm sorry. But sometimes we have to spend a lot more time than an hour on something before it makes sense. That's just kind of like learning. So hopefully maybe you'll ponder that. But there was a moral of why I spent all that time doing that. And what it motivated, or what at least I tried to motivate, is that some events must depend on other events. You know, so I use these kind of examples, but here's a good way to think about it. If I just said, okay, I want to know the probability that the starting salary for a college graduate is going to be greater than, say, $60,000. Well, there could be lots of varying sort of good answers to that. And the problem is in many things that we study in the real world, we need context. Because if you're taking a job in New York City, it is very likely that your starting salary is much higher than your starting salary if you're taking a job in Pittsburgh. And your starting salary in Pittsburgh is probably much higher than if you're taking a job in the middle of Wyoming. And there's lots of reasons for that. Things like cost of living and taxes and all kinds of different things that affect something like that. We also see that if we have a deck of cards and I'm going to pull 3 cards out, I'm going to pull one, set it down, pull another, set it down, that I would imagine, at least intuitively, that the likelihood of selecting a certain card on the second and third try is going to depend on what I pull the first time. Because the first card I pull was no longer in the deck. So if that card was black, there is one less black card in the deck now. If that card was a heart, there was one less heart in the deck now. So we need a way to define how that should behave, but also keeping in mind that we have these sort of axioms of probability that we want to adhere to. So luckily for you guys, there was this real smart guy. His name was Kolmogorov. He even wrote a book back in the 1930s. Actually, maybe not lucky for you because he's making your life miserable right now, because if it weren't for him pretty much inventing the theory, not inventing, but formalizing the theory of probability, you guys wouldn't have to take this class right now. But what Kolmogorov realized is that there is a very useful way to develop a theory of probability. And so one of the things that we need, and I alluded to this last class, is we need this thing called conditional probability. Does anybody have a question? I hope not, because I haven't done anything other than give it a name. So if you go back to what we did on Monday, I drew this tree. And the point of that tree was we had these branches. And then everything that happens further down the branch, the likelihood of that happen is completely dependent on what happened previously. That was the point of drawing that tree. We'll let you think. We'll let you think. Do you want to say anything? Do you want to say anything? It's supposed to give you 10 seconds, right? Katie's just like, I want to just do problem 7 already, O'Grady. Quit. Actually, I shouldn't say that. That's not how you talk, right? Do you talk that way? All right. Going once. Going twice. Sold. Okay, here's what we define the following sort of situation. I get a clean slate here. So let A and B be any 2 events. In a sample space S. So the probability of A given B is defined by the following formula. P, and we're going to use the notation A getting sloppy. We use a vertical bar, B, and this by definition is equal to the probability that A occurs and B occurs divided by the probability of B. So notice that the first thing that you should think about is that this doesn't make sense both definition-wise and intuitive-wise if the probability of B is not equal to 0. Because you can't divide by 0, right? So this doesn't make sense if you're dividing by 0. But of course, if the probability of B is equal to 0, then this doesn't make any sense anyhow. Because it doesn't make sense to talk about A happening given B if B can't happen. Like if B can't happen, it doesn't make any sense to say, well, let's wonder what happens. Let's wonder how likely A is given B. And by the way, I should also point out how this reads. So you should read this A given B. Now, here's what's pretty cool about what we did on Monday. And again, I hope that you'll spend some time to maybe think why would O'Grady say this other than he's some weird nerd? But I really ain't. Am I? I don't know. My friends think I am. But I do think it's interesting and quite fascinating, because what we did on Monday, is we drew this tree about this card game, sort of this drawing 3 cards. And Tyler, I think I don't know if you're there, hopefully you are. You had suggested you thought you understood how it worked. And what's cool about what you said is that using this definition, our intuition matches what we think should happen. Because if we rearrange this, we obtain precisely what you suggested. We get that the probability that both A and B occur, the probability that 2 events occur, is equal to the probability that first B occurs times the probability of A given B. I mean, put this sentence next to that tree. So we're going to do that again in a second, but let's think about it in terms of 2 events. Let's suppose A is the event that I get a head on the first toss and a head on the second toss. Well, it's kind of redundant, but that does hold here. Does the probability of my second toss have anything to do with my first toss? No, right? That coin doesn't know how many times. So the probability I get a head, given that I had a head, is still the same probability, but this formula holds. What would you get? You'd get a half times a half, as you'd expect. We're going to do an example of this. You've sort of done it for your homework, but this is giving us a shortcut, is what I'm saying. Because when we wanted to answer questions about coin tosses before, we had to write out the sample space. And then we had to count how many of these things, how many elements were in each event. And so that's a tedious thing. But what this is telling us is no. A shortcut would be you multiply things together. In terms of our card game from last time, let's just think about the first 2 steps. Say we get a black card and a black card. Well, this is telling us that the probability we get 2 black cards in a row is first the probability you get a black card, then the probability you get a black card given you already had a black card. So in English, this is saying exactly what we thought when we had our intuition yesterday. Now, I shouldn't say we had our intuition, because I said, I sort of says, does anybody have anything, any thoughts on this? And you guys, of course, as all great students do, you look at me and say, and you roll your eyes, make those faces like Trump was making last night, and go, and then you say, get out of here, O'Grady. But no, actually on Monday, one of you, and again, I keep calling on Tyler, I think it was you. I could be wrong if it wasn't. If it isn't, I'm sorry, but I'm pretty sure it was you. You said the trick is to multiply them together, and that's exactly what this is saying.
You're talking about whenever I said it was like out of 52 cards, and I said you take the top number, and then the next one you take, I don't know the example. Oh, 26 out of 52 times.
You follow the branch of the tree.
Yeah, 26 out of 52 times 25 out of 51. Right.
So what this means then is instead of having to draw that whole tree out, or instead of having to write out sample spaces, whether it's for decks of cards, or whether it's visualize a dice game, or whether it's visualize us tossing a coin 3 times, what this is telling us is this is a shortcut. So that's the first thing. So let's put it right in action. Let's stop all the scary symbols and let's put it right back into what we were doing. So maybe I'll go back there. You might be copying this down. I'll take a sip of the agua. Oh, by the way, today is the 30th, right? I think your quiz 1 is officially due today. So if you didn't do quiz 1 yet, take 5 minutes of your life and do it. It's on Canvas. It's not hard. Was it hard? No, it's easy. Maybe, did you do it yet, Dante? Did you? Did you turn the homework in? Did you? I'll believe that when I see it. Lots of you owe me homework is what I'm saying. Not all of you, but lots. All right, let's get this right in action. So back to problem 6. So let B equal the event we pick a black card. Well, the probability that I pick 2 black guys in a row is the probability that I first choose a black card, followed by the probability that I choose a black card given my first card was a black card. And so if we remind ourselves how many black cards are in the deck, well, there's 26 black cards, there's 26 red cards. So the probability I choose a black card is 26 out of 52. And then if I've already chosen a black card, there's 1 less black card left. So there's now 25 black cards for the second time, and there's 1 less card total, so there's 51 left. And of course, you can do the arithmetic on a calculator if you'd like. That's what I'll do because I don't want to do this like it's 3rd grade. So if I take 26 divided by 52 and I multiply it by 25 divided by 51, you end up getting, just doing some simple mathematics, what? 25, cancel that, 26, how's that? Yeah. So 26 over 52 is what number? 1/2, right? Make it easy. So really, this is just 25 divided by 102, which of course you can approximate as a decimal, say 0.245, or if you'd like, 24.5%. So that's the probability that I pick my first card to be a black card, my second card to be a black card. But that's not what the question asked, really. The question asked if I get 3 black cards in a row. I think that's what it asked, right? Or was it? I'm actually going to pull the homework up, homies.
Yeah, it was 3 black cards in a row.
And so we could put this over here so we're not taking up too much space. Thus, the probability that I get 3 black cards in a row, we can write it out. It's 26 over 52 times 25 over 51 times 24 over 50. And this time I will not do it in my head because that's silly. I will do it in a calculator. So this simplifies the 2/17, which is approximately 0.1176. Or if you'd like, what is that? 11.7%. Does anybody have a question about this part? Now, it might be worth our while to sort of take a slightly simpler example, but let's finish this one first. All right, so the next question was, what about all spades? So let S, well, that's a weird L. So let S equal the event. We pick a spade. Well, the probability that I choose 3 spades in a row would be the probability of what? Well, we could sort of break this down. I mean, if we have, you can imagine that even though it works for 2, that we can generalize this. So instead of writing the scary stuff down, let's just write the numbers. How many spades are there to begin with? There's 13 out of 52. And then if I get a spade again, I'm down to 12 out of 51. And then 11 out of 50. And so if I go and do the math here, we end up getting 11 over 850, which is approximately what? What is that in percent? So if I divide, I gotta quit trying to do this in my head. 0. 0.1294. So what is, oh, I forgot a 0. That's bad. Let me rewrite this. That's ugly. So it's 0.0. Now, what is that in percent? Well, in percent, you move the decimal point over 2. So it's like what? 1.2 or 1.3%. You want to, depending on how you want to round. All right. Does anybody have a question about this? Now, much like the first 2 parts of problem 6 were to motivate some new topics, problems C and D are also there to motivate some ideas. How would we know at least one king? That seems like a sort of a difficult thing to answer. We would have to literally write out every hand and count how many ones had one king, right? That seems very, very difficult. So luckily, we thank our boy Kolmogorov and the nerds who invented measure theory and hence the theory of probability. And they realized that if we use those three axioms, we can creatively figure out how to answer C and D without actually having to do a lot of work. So those axioms give us a workaround. And to motivate the workaround, let's imagine if I say that it's going to rain and it's a 30% chance of rain, that the intuitive thing that you would say is, well, there's a 70% chance it doesn't, right? So there's a name we give for an event and not that event. So if there's an event that it rains, then the opposite of that is that it doesn't. And so there's a fancy name for that. It's called the complement. And it turns out that we can use this idea to sort of facilitate simpler ways of answering questions. So to answer 6, C, and D, it's best to learn new things. Now, I don't want to spend an hour motivating them like we did last time, because we can't do that with everything. But we can sort of think about this. So let A be any event. We define the complement of A So let's think about how we would do this. How would we define, if the one event is that it rains, how would we define the event that it doesn't rain? Well, in English, we would say not A. So how do we denote it, though? Well, there's lots of ways to denote it. So we can denote the complement by, some people do A with a bar. Some people do A with like a power C. Some people do A with like a, what we call like an apostrophe, or this like prime. And some people use this notation. It's like an upside down L. I don't remember what our book uses. Anybody know? Doesn't matter. We can use them all. Here's a cool fact, though, that can be deduced by our axioms. Once again, thank you, Kolmogorov, for axioms. Let's all say thank you, Kolmogorov. One of the most famous. Let's look him up just while we're taking a break. It's always great to have a nice break in the action. And see, I don't even have to really go far, and they already know who he is. Isn't that cute? And a Soviet mathematician, the enemy of the good guys, right? Isn't that what they say in the Cold War? I wonder if they teach that in Russia. I don't know. But anyhow, there he is, a true legend. Notice that he did significant contributions to probability theory. Now, he was quite a legend. But anyhow, look at him go. So luckily, a lot of smart people sort of came together and figured this out for us. And of course, let me remind you of another thing. Some of you are like rolling your eyes, even if you're actually paying attention, like, oh yeah, okay, because anybody in the real world gives a damn about card games and coin tosses. Need I remind you, fools, and I say that lovingly, I love you all platonically, that the point is, there's no way we can understand the real world if we can't understand simple experiments that we can do. The fact of the matter is, in the real world, we try to take these ideas that help us understand card games and dice and coin tosses and apply these ideas to real world things like stocks and survival rates on medicine and insurance quotes and all that kind of stuff. Predicting weather, etc. All right, so here's what's really, really cool. And hopefully you will appreciate it. We can do the following. And that is that the probability that a complement occurs, and this is intuitively clear as day, is 1 minus the probability of the event. So don't overthink this. The probability that it doesn't rain is equal to 1 minus the probability it rains. The probability I get a head is equal to 1 minus the probability I get a tail. So let's not get it twisted. Let's not get it confused. We'll first put this in a box, and then we'll do a couple quick examples right underneath it so we can get it all down pat. Examples, the probability it rains. Is equal to 1 minus the probability it doesn't rain. The probability of heads equals 1 minus the probability of tails, assuming I'm flipping a coin once. Now, let's apply this to our homework. I am picking 3 cards. The probability of at least 1 king is equal to 1 minus the probability. What is the opposite of at least 1 king? No kings, right? In the context of the problem 6. Think about it, and we'll slow down and check it out in a moment. Let you think about it. If you have a question, please ask the peoples.
So can you use the same theorem for rolling a die too?
Yeah, for example, problem 4, this would probably be the way to go.
Okay.
I mean, look, you could torture yourself and write it all out, but that's not how we want to operate. And then and Tyler, even to think about it in the real world, think about how we would do things. I mean, if we want to understand the result and likelihood of certain things, we realize that often one event might be impossible to study, whereas the other one is something we can easily identify. Or we might be able to collect data on one event, but not on its complement, type stuff like that. So let's think about why this is true. So if I have at least one king, that means I have a king, 1 out of 3, 2 out of 3, or 3 out of 3. So the opposite of that is none, no kings, right? Does that make sense? I think. All right, so now we can solve problems 6C and 6D because they're very much the same. So I love motivating ideas through homework. What a time to be alive. So back to, oh, that is a sick looking thing right here. So back to number 6 on the homework. What homework is this? 3, right? Homework's 3. So for part C, the probability of at least one king, is that what I asked for you? Is 1 minus the probability of no kings. Okay, so what would that be? Well, we have to reason this. So the first card, what is the probability we don't get a king? Well, how many kings are there? There's 13 of each suit, and there's a king in each suit, so there are 4 kings, right? That was a weird way to think about it. I know I did it the long way. What the hell? I was like looking at myself. I'm like, why do I think like that? But that's, everybody thinks differently, right? That was a really weird way. I do that to show you that there's no correct way all the time. Everybody can have different ways. So there's going to be 3 things we have to choose here. The first one is, if there's 4 kings, that means that there are 48 non-kings. So there's 48 out of 52 for the first choice. And then there's still 4 kings in there. I want to miss them, so I have to have 47 over 51, and then 46 over 50. That is how I dodge all the kings. So take a moment to ask yourself if you have any question about that, or if you want to ask me, or you just want to mutiny. Yes, Katie, what's up? Yeah. Well, you don't even need to, because, well, okay, so that's actually a different, well, hold on a second. We'll get back to that. That's a good question. Let me just finish this problem, and then and then I'll explain to the viewers at home what Katie asked, and we'll talk about it. So let's just finalize this particular creature. So again, why is it 48? Because I'm trying to dodge the kings, and there's 4 kings out there. So any other of the 48 out of 52 is good. So by the way, if I do this correctly, I get 1 minus 4, 3, 2, 4 over 5, 5, 2, 5. And a little more arithmetic takes us home. This becomes, I like to keep things in fractions as long as I can. That's just the old school in me. So there's approximately a, let's say, 22% chance of getting at least 1 king. So before we get to Katie's question, Does anybody have a question about this? Okay, so this is one way to solve the problem. It turns out there's other ways of doing it too, but this is one way of doing it. And when we learn some other counting things, now, Katie asked in problem 4, is that what you asked? So if you ask on problem 4, say I roll a fair dice is rolled 3 times. I want to know the probability that I get exactly 1/5. Now that's a little more difficult, right? So that one, at least right now, you might have to actually write out these probabilities. Now, you can use that theorem if you sort of think of it from a different way. So what I mean by that is, so roll 1. So we could still use this multiplication idea, right? So really, what that thing tells us, and we'll define another idea, is that the shortcut that we could have used in even the problems going back is, if I'm going to flip a quarter 3 times, then I can look at the probability at each stage and multiply them together, and I get the same answer. And the same thing goes with rolling dice. What's the probability you get a 5 on the first roll? Well, that's 1/6, right? What's the probability you get the 5 on the second roll? That's 1/6. But you don't want a 5 on the second roll, right? So that's a little more, that problem's a little more involved, and it also helps motivate some ideas that we can think about. So let's actually jump into that problem. But before we do that, we want to make an idea about this sort of definition of conditional probability. Does anybody else have a question about problem 6, though? I mean, you now know how to do problem 6. We did A, B, and C. Part D is almost identical to C. And I know a lot of you are going to say, well, we already turned this in. Well, that was the point, right? What good do I learn from you if I do all the problems and then you can submit them, right? Then you just copy down what I tell you. That doesn't teach me what you know or don't. And you'll get a chance to remedy any of that anyway. Okay, so here's a cool idea that we can sort of generate from so the definition in theorem about conditional probability these suggest other sort of shortcuts. Now, again, I don't want to go ahead and derive all these things, but it's worth at least seeing how they're in action. So we defined this term before, this idea of mutually exclusive. We kind of said it in passing when we defined our axioms. So So if A and B are mutually exclusive, now I'll remind you of what that means. They can't happen at the same time. Then what can you think that we can say about their probability? Well, the probability would be that the probability that both A and B would happen, that would be 0, right? That makes sense. If they can't both happen, I mean, for example, if I toss a coin once, what's the probability I get a heads and a tails? Well, it's 0. If I roll 2 dice, what's the probability that I roll 7 and my roll is even? 0. It doesn't make any sense. If we drop the mutually exclusive, and we don't have to, but if we drop it, we obtain another useful formula, that the probability that A or B happens is equal to the probability of A plus the probability of B. And then we have to be careful because we have to subtract out that the probability that they both occur. So again, these sort of formulas, I'm not suggesting you memorize them, but these are all formulas that can be deduced from the axioms. And they're extremely useful because they give us shortcuts for computing certain things.
So can you do a problem now with using this formula just so we can?
Yeah, we're going to do that in a second.
Okay.
Yeah. So we're gonna use this to talk about problem 4 in a minute. But we need to talk about one more thing, another definition, and that is if the probability of A and B happens to be equal to the probability of A times the probability of B, we say A and B are independent. So this is a word you want to be sort of curious about and understand. Now, let's think about these things for a second. And let's put them in the context of problem 4. Now, I said a fair dice, and that might seem misleading, but what I meant is So I mean the following. So this is homework 3, number 4. So let's imagine that I roll the dice. And I want to know the probability that I get exactly 1, 5. Now, there's lots of ways that can happen. But we understand what they are. Now, I can't use the idea where the complement, because what's the complement of 1, 5 exactly? Well, that would mean what? That could mean no 5s. That could mean 2 5s. That can mean 3 5s, right? So I could maybe attack it that way. But is there any other way that I could attack this problem? Now, here's what's going to happen. Some of you might Google these problems, and you probably see things you haven't seen before. They probably see these weird symbols. They're called binomial coefficients and stuff, and you don't know how to make sense of it. We're building to that. But let's try to reason this. Without having to, or, you know, it doesn't hurt, I guess, to build intuition by looking at the sample space. So if we look at the sample space here, let's imagine I have 3 dice. So I'm going to think of each roll as like, I'm going to list them in a pair. So So let's look at one way of doing this. So in rule 1, so we can have a, what can we roll? We can roll 1, a 1, and a 1 with 3 dice. Then we can roll a 1, and a 2. And we can roll a 1, and a 3. And we can roll a 1, and a 4. And then we can roll a 1, and a 5. And then we could lastly roll 1, 6. Oh, that seems like it's going to take forever to do this, right? And then I could say, okay, what about, let's put the next idea. What if I have a 1 and then a 2 and a 1, and then a 1 and a 2 and a 1. And of course, at some point, you're like, yikes. You don't want to do this. But there's got to be a way that we can use our axioms in the form of these sort of formulas we listed to deduce something. Does anybody have any thoughts? Not that you necessarily have to, but okay, so is there another way to ponder this? So let's imagine that we get, you know, what are the ways in which we can get 1, 5? Well, we can get 5, no 5, no 5, right? So let's think about this. So we'll list it like this: rule 1, 2, 3. So we can get 5, no, no. We can get no, 5, no, correct? So think of this, and maybe this is not clear how I'm doing this, but I'm imagining that, you know, the first column is rule 1. So maybe I should draw this a little different. Maybe this notation is scary. So let me redo this because it might not be clear to those at home or even in here what I'm trying to do. So let's call this row the rule. So I have 3 rules. Rule 1, I can get a 5 and then no and no. Rule 2, I can get, excuse me, in the second scenario is I don't get a 5, then I get a 5 and I don't get a 5. But the question is how this can happen more than one way, right? Because there are 6 options here and there are 6 options here. Except there's not. There's actually only 5 options here because I can't get a 5. Because if I get a 5 here, then I'd have 2 5s. If I get a 5 here, I'd have 2 5s. So the question you then ask yourself is how many ways can this happen? So the probability that you get a 5 on the first roll is 1/6, but the probability you don't get one is 5/6. So before we go any further, does anybody have a question? Anybody in the peanut gallery? No. So we need to think about what are the options. So if we think about probabilities being associated with these, so the probability, say here, would be, well, let's go to the next page. So So if I get a 5, the probability of a 5 is 1/6. Probability of no 5 would be 5/6. Does that make sense? Now, thus, the probability 5 no no we would expect to be 1/6 times 5/6 times 5/6. The probability of no 5 no would be 5/6 times 1/6 times 5/6. And then the probability of no no 5 we would expect to be 5/6 times 5/6 times 1/6. Now, why is this legal? First off, this is legal by the theorem that we said before, because look, the second rule doesn't care what happened to the first rule. And the third rule don't care what happened on the first or second. It's not like we're selecting cards where one's not there anymore. So these events are all independent, which means how do we compute the probability? We multiply them together. So what is this number equal to? Well, all these are the same thing. Every one of these is 25 over 6 cubed, which is 216, I believe. You know. Now, each one of these events is mutually exclusive. You can't have two of these things happening at the same time. You can't do 5 no no and then no 5 no. So, and again, this is difficult for us to gather in the first. It's very overwhelming right now for us. We feel like there's just formulas. We don't know which one to use. That's natural. This is new to you. You're trying to learn something, right? No different than if I put you in an airplane right now and dropped you off in Moscow. If you don't speak Russian and you ain't got a smartphone, you're in trouble for a little bit, right? You're trying to learn something. You don't know the language. Well, unfortunately, mathematics is a language. This is a language. You're trying to learn ideas in a language that is unfamiliar to you. So the last thing we could do, we can finish this because it's not going to take long. And so here's what we have. So since 5 no no, no 5 no, and no no 5 are mutually exclusive, we have the probability of exactly 1/5. That's ugly. That's equal to the probability of 5 no no plus the probability of no 5 no plus the probability of no no 5. And of course, every one of these is the same. So you have 3, and it's 25 over 216, right? I think. Let's double check. Yeah. And of course, if you recognize that 3 goes into 216, because 216 adds up to 9, then you get that this is what, 25, 7s, carry the 72s. And by the way, I ain't expecting that you can do arithmetic as quick as I am. That's fine. I got years of practice. But what you can do is you can use a calculator. And so barring that I didn't make any mental errors, which I don't think I did, we end up getting 34.7%. Be out of here in 1 minute. No, we're lapping up now. So you can, yeah. Yes, ma'am. All right. So does anybody have any questions? All right. Well, let us end this party. Hopefully you'll study this example. It's challenging, but it is one that you should know. And by the way, once you learn how to do this, it's not that difficult, but learning it is the problem. All right, guys, thank you very much. I appreciate it. I will talk to you guys next week. Please email me with any questions. Thank you.